Let's look at another practical example of domain and range. Suppose Denver's Mile High Stadium is capable of seating 63,026 fans. For each game, the revenue R, which is the amount of money that the Broncos organization makes, is a function of the number of people N in attendance. If each ticket costs $30, find the domain and range of this function. All right, so let's start by identifying the independent and dependent variables. And the reason we want to do that is that the domain is looking at all the possible values of the independent variable, and the range is looking at all the possible values of the dependent variable. So the problem says that the revenue is a function of the number of people. In other words, the revenue depends on the number of people. So our dependent variable is that revenue R, and the range would be all the possible values that revenue could take on. And since that revenue depends on the number of people, that means our independent variable is the number of people, which we represent with the letter N. And that would be, our domain would be all the values of the number of people we could have at that game. All right, I'd love for you to pause the video and give this a try. All right, so hopefully you gave that a try and you came up with some ideas or some answers there. Let's check them and see if we came to the same conclusion. So the smallest number of people would be 0. So either nobody showed up for the game, maybe there was a power outage, but there's nobody there. And then that would be our lower bound. And then our upper bound, assuming that we're following all the rules and regulations, is this 63,026. Right, and then our range. So if I look here, if nobody shows up, then I'm not going to make any money. So probably the lowest value here that I would use for R is 0. And then my upper bound, what if the stadium's full? All 63,000 plus people came and they each paid $30. That would be the upper bound on my revenue. So it's 63,026 times 30, which means that the upper bound on their revenue is 1,890,780. All right, so we have another example here. This one has both an equation and a graph. So it says a sunflower plant is measured every day, little t, so little t represents each day, and they're defining little t to be greater than or equal to 0. The height h of t, which is measured in centimeters, of the plant can be modeled by the logistics function, which is graphed below. So we have this picture here, and then we also have this function here. The nice thing about a logistics equation is that there's a natural point at which the plant doesn't get any taller. Okay, and that's that upper bound here on the height of the plant. And that's known as what's called a carrying capacity. So it's a natural limit that occurs just based on nature and science. All right, so our independent variable here is this one on the horizontal axis. So that's little t. And our dependent variable is going to be h. Okay, so let's start by looking at that dependent variable and getting the values of our range. So h, if we look at this carrying capacity, that's our upper bound. We can see that that's 250. That's kind of where our function level's off at. And then the lower bound for the range, if we're looking at this graph, we see that it's not quite 0. But we do know that the smallest value of little t is 0. And this graph is increasing. So this will be the lowest value here. And we can find that by plugging little t equals 0 into our equation here. So I have 250 divided by 1 plus 24 to the 0.9, or 24 times 0.9 to the 0. Anything to the 0 is 1. So I have 250 over 1 plus 24, since 24 times 1 is just 24. And that gives me 250 over 25, which is 10. So the lower bound on my range is 10 centimeters, and my upper bound is 250. And then let's look at the domain. So the problem gives us the lower bound for our domain. Little t is greater than or equal to 0, so 0 is our lower bound there. And then there is an upper bound. If we think about this, that sunflower plant at some point is going to die. So it's not going to keep growing any longer. And so what we'll do is we're going to define big T to be the time the plant dies. Okay, and so the plant is going to be alive from day 0 until whenever it dies. So little t, the number of days that plant is growing, is between 0 and big T. Okay, so this probably seems like a little bit of an odd thing to do, but it's a common trick used in science and physics. If there's some unknown, but there's a natural end to the domain, so the plant dies or something along those lines, we'll define it with a variable like this capital T. And what that does is it allows us to analyze the range on this kind of practical consideration of the domain. All right, so come back to the next video, we'll look at kind of some more uses of graphs to find domain and range.